Hey there and welcome back to the channel. Tonight the story stretches far beyond the Milky Way into a universe packed with countless galaxies, countless stars and more worlds than imagination can hold. The real question is not whether the ingredients for life exist out there. The question is how often the cosmos repeats the conditions that let chemistry become something living. If this kind of deep calm science journey is for you, please tap like, subscribe and turn on notifications so these long immersive episodes keep coming. Now let everything slow down and let the universe do what it does best. Reveal its secrets one quiet layer at a time. A spiral galaxy turns slowly in darkness with pale arms and long dust lanes that cut the starlight into soft shadows. The core idea settles early and quietly. If the physics and chemistry that allow life are common, then life beyond the Milky Way becomes statistically plausible. The question shifts away from romance and toward repetition. In the dim band of a spiral arm, matter does not announce itself. It arranges itself. Fine grains drift and gather, gas cools into thin sheets, gravity shapes curves and knots. In that steady choreography, the ingredients of biology do not look rare. They look routine. A first small unlock appears in the dust lanes themselves. Dust is not dirt in a simple sense. Dust is a collection of heavy atoms wrapped into tiny solids. Those atoms must be made. In stellar interiors, light elements fuse into heavier ones. Carbon forms, oxygen forms, nitrogen appears through other chains of reactions. When stars age and lose material, those atoms escape into space. They mix into new clouds. The galaxy's dark streaks are evidence of that mixing. The same process operates wherever stars live and die. At this distance, life is not a single spark. Life is a possibility written into chemistry that repeats. The spiral arms carry another slow clue. They are not uniform bands. They are layered regions with gradients. Dense clouds sit beside clearer gaps. In the densest parts, gas cools and thickens into cold molecular clouds. Inside those clouds, the light dims, the temperature drops, surfaces of ice and dust grains provide places for atoms to meet. Simple molecules form, some become more complex, carbon chains lengthen, oxygen joins in new arrangements. This does not guarantee biology, it does something simpler. It shows that complexity can begin in darkness long before any ocean exists. The galaxy becomes a wide chemistry lab without walls where reactions happen slowly and persistently. That idea matters because it removes a hidden assumption. Biology does not need to start from nothing on a single special planet. Prebiotic chemistry can be spread across a galaxy, then carried into many forming worlds. A gentle scale shift follows that thought. One dust grain is smaller than a cell. A cloud is larger than a star system. A spiral arm is larger than the cloud by orders of magnitude. Yet the same few elements keep reappearing across each scale. Carbon bonds, oxygen reacts, hydrogen saturates, nitrogen stabilizes. Those behaviors are not local habits. They are properties of matter. The galaxy's light contains signatures of those properties. Certain wavelengths are absorbed, others pass through. The patterns repeat across many environments. A second small unlock arrives in what those patterns imply. If the same elements appear in distant galaxies, then the raw inventory for familiar chemistry is widespread. Life may still be rare for other reasons, but scarcity of ingredients becomes a weaker explanation. The probability question then turns toward worlds. A planet is not required for chemistry, but a stable environment helps chemistry organize. Around young stars, disks of gas and dust flatten into rotating planes. Within those planes, solid grains collide and stick. Pebbles become larger bodies. Larger bodies clear paths and gather material. Over time, stable orbits form. Some worlds remain rocky. Some become rich in gas. This sequence does not rely on a special location. It relies on gravity, angular momentum, and time. Those are not regional preferences. They are universal constraints. A calm analogy fits this stage. In a slow river bend, eddies appear again and again. The water does not choose them. Flow and shape produce them. In the same way disks tend to produce worlds. The details change, the tendency remains. That tendency matters because it expands the search space without invoking fantasy. A third small unlock follows from simple multiplication. If planets are a natural outcome of star formation, then the number of potential habitats becomes enormous. The universe contains hundreds of billions of galaxies. That is a number so large it becomes smooth like a horizon. It's comparable to counting every grain in a vast beach, then finding that each grain belongs to its own coastline. Even if only a small fraction of stars host worlds with long-lived surface water, the absolute count can still be immense. This does not claim life exists elsewhere. It claims that the stage is not small. The stage is so large that even rare events can happen many times. The idea becomes stronger when time enters. Life on Earth appears relatively early once conditions stabilize. That fact does not reveal the exact difficulty of abiogenesis. It does suggest that biology may not require a chain of extremely unlikely steps. It suggests that given steady energy, liquid solvents, and chemistry organization can begin. In the early Earth, the first life remains hidden behind deep time and altered rocks. Yet the timeline points in one direction. Biology is not delayed until the last possible moment. Biology begins when environments permit persistent chemistry. That matters because other galaxies contain environments that are older than the Sun's neighborhood. Some systems have had long spans of stable time. In a universe where time can stretch across billions of years, long spans are common. Continuity can do what intensity cannot. A fourth small unlock arrives as expectations become more precise. Life does not need to be complex to be meaningful. Microbial life dominates Earth for most of its history. Complexity comes later and remains fragile. Simple life, by contrast, can occupy many niches. It can live in water-rock pores, ice pockets, and chemical gradients. This widens the category of possible habitats. It also softens the demand for perfect Earth-like conditions. The idea becomes a quiet reframing. The probability of life depends on the probability of stable chemistry, not on the probability of advanced intelligence. The first may be far larger than the second. A limit appears here, and it rests on observation rather than imagination. Intergalactic distances are immense. Light weakens with distance. Detail collapses into averages. A distant galaxy becomes a blended glow. Its stars merge into one spectrum. Individual planets vanish into the background. That does not erase the reasoning. It changes what evidence can look like. Direct detection of life in another galaxy is beyond current reach in practice because the signal from one world is drowned in the light of billions of stars. This is a specific boundary of measurement. It is not a boundary of possibility. It means that a probability must be inferred from universal processes. It means that the argument is built from chemistry, planet formation, stability, and time. Those are visible in the large-scale behavior of galaxies even when individual worlds remain invisible. The spiral galaxy continues to turn. Dust lanes keep their curved edges. Star-forming knots brighten then fade as gas disperses. Nothing in this slow motion suggests a special exemption. No feature announces that biology is forbidden beyond one spiral. The most cautious conclusion stays calm. The universe appears capable of producing the ingredients and environments that life requires far beyond the Milky Way. The remaining uncertainty lies in how often those ingredients cross the threshold into self-sustaining biology. Beyond the galaxy's outer arm, darkness becomes thinner. Between galaxies, faint gas stretches in filaments. The next step moves into that quiet space where matter is sparse but still active. Between galaxies, space looks empty until light reveals a faint structure. Long filaments stretch like pale smoke across a darker background. The early idea is simple. Even the gaps between galaxies carry matter and chemistry, so isolation is not complete. In a quiet filament, gas forms a thin gradient. Denser threads fade into softer edges. Tiny grains drift within it. At this scale, motion is slow. Gravity pulls gently along the filament's length. A small unlock appears in the word between. Between does not mean nothing. It means low density. In many regions, only a few atoms occupy a cube of space 1 meter on a side. That sparsity still matters. A few atoms can carry carbon, oxygen, and nitrogen in trace amounts. Over immense time trace becomes meaningful. A visual anchor settles on a filament connecting two distant galaxies. The bridge is not solid, it is layered. Patches of slightly denser gas sit inside a more diffuse haze. In those patches, collisions happen more often. Cooling happens a little faster. Molecules can form on the surfaces of drifting grains. This is not a promise of life, it is a reminder that chemistry is not confined to planets. The first core concept takes shape as the cosmic web. The cosmic web is a network of filaments of gas linking galaxies. The definition stays short. The web guides where matter flows over cosmic time. The analogy becomes a drop of ink in clear water. The ink does not leap. It spreads. It threads through the fluid in faint streaks. It reaches places that look separate at first glance, in the same way enriched gas spreads through the web. A second visual anchor arrives in the outer halos of galaxies. Around a galaxy, gas extends far beyond the bright disk. The density falls with distance. The temperature changes with depth. Some regions are warm and thin, some are cooler and slightly clumped. In those halos, heavy elements escape from stellar life cycles and drift outward. The physical detail is gentle but concrete. Boundaries are not sharp. They are gradients. A smooth fade replaces a wall. That fade matters because it allows mixing. The second core concept is chemical enrichment. Chemical enrichment is the build-up of heavy elements made by stars. Those elements do not stay locked inside one galaxy forever. Gas can be pushed outward during energetic episodes. Gas can be pulled along filaments during slow accretion. In both directions, the web becomes a carrier. Another small unlock appears here. Life needs more than hydrogen and helium. Rocky planets need heavier elements. Organic chemistry leans on carbon and oxygen. If enrichment reaches intergalactic space, then even young galaxies can receive a starting inventory. The web becomes a shared reservoir. A slow-scale shift follows. A dust grain is tiny. A halo is vast. A filament can span millions of light years. Across that span, the same few atoms repeat their bonding rules. Carbon still forms chains. Oxygen still bends angles in molecules. Nitrogen still stabilizes certain structures. The rules do not weaken with distance. Only the pace changes. The pace is the third quiet character in this section. In sparse gas reactions can take a long time. Collisions are rare. Energy is spread thin. Yet time in the universe is immense. Slow processes still accumulate. Molecules can form a break and form again. Grains can collect icy layers, then lose them, then collect again. The layers leave faint chemical fingerprints. A third visual anchor appears as a thin veil of ice on a grain. The coating is uneven. It has micro ridges and tiny pits. Atoms land and stick. Some hop away. Some meet and react. Complexity grows in increments. This does not require a planet's ocean. It requires surfaces, low temperatures, and persistence. A limit of intuition arrives softly. Human intuition expects emptiness to mean inactivity. Intergalactic space contradicts that expectation. Activity is present but diluted. A limit of observation follows as well. Most of this gas cannot be seen directly because it is too faint. Evidence arrives indirectly. Light from a bright distant source passes through a filament. Certain colours are absorbed. That pattern is called an absorption line. An absorption line is a missing slice of light at a specific wavelength. One sentence is enough. The missing slice reveals where atoms lie in the path. Two sentences return to plain language. A faint notch in the spectrum can signal carbon. Another notch can signal oxygen. One sentence closes why it matters. Chemistry can be mapped where no glowing cloud is visible. Another small unlock grows from this method. It shows that heavy elements exist far from stars. It shows that galaxies share their products. It also shows a boundary. The pattern usually gives averages along a long path. It does not reveal the conditions around a single world. It does not separate one small pocket from the next. The web is seen as a layered fog, Fine details remain hidden. That boundary matters for the life question. If life exists outside the Milky Way, the closest evidence may come from atmospheres and surfaces of planets. Those signals are tiny even in nearby systems. In other galaxies, a planet's light is drowned by starlight. The intergalactic medium becomes easier to study than individual worlds, even though it is thinner. The irony is quiet. The largest structures are clearer than the smallest clues. A fourth visual anchor settles on a galaxy cluster where many galaxies share a larger pool of gas. The gas between them is heated and stirred. Gradients form across the cluster. Denser pockets sit near the center. Thinner gas extends outward. In such environments, mixing can be efficient over long time. This adds another subtle point. Chemistry does not only spread by calm diffusion. Large-scale gravity can churn reservoirs. The same ingredients can be redistributed, then reused. A calm consequence follows. If the universe spreads life's raw materials through filaments and halos, then many galaxies begin with similar building blocks. Differences still exist. Some regions are metal poor, some are rich, some are harsh with radiation, some are calm. The web does not guarantee habitability. It supports the idea that chemistry is widespread and shared. That support strengthens the statistical argument from the previous section. The stage is not only large, the stage is connected. The final thought leans toward the next step. Filaments deliver gas into galaxies. That gas settles into rotating disks around newborn stars. In those disks, grains collide and grow. The path moves from intergalactic fog to the sharper rings and gaps where planets begin to take shape. A newborn star sits inside a thin rotating disk that looks like a pale coin of mist. The early idea lands without strain. Where a star forms leftover material often settles into a disk. That disk naturally tends to make worlds. The disk is not smooth. Light and shadow reveal rings and darker gaps. Some edges look sharper than others. A faint warp can cast a curved shadow across the outer layers. That physical structure matters because it shows order emerging from motion long before any planet becomes a finished sphere. A first small unlock appears in the disk's flatness. Gravity pulls inward from all directions. Rotation resists collapse in the plane. The result is a thin layered sheet rather than a ball. Gas and dust share the same rotation but not the same behavior. Gas flows and swirls, dust settles and drifts. In the mid-plane, grains move through a slightly thicker fog of gas. Collisions happen gently at first. Tiny particles stick by weak forces. A second visual anchor appears as a band of dust along the mid-plane. It looks denser. It looks darker. It absorbs more light. That band is a nursery for growth because it is sheltered and crowded. One core concept takes shape here as a protoplanetary disk. A protoplanetary disk is a rotating disk of gas and dust around a young star. The definition stays short and then returns to plain language. In a calm disk, particles do not need a special push, they need repeated contact. A single collision does little. Many collisions over time build larger clumps. The everyday analogy becomes a snowdrift forming in steady wind. No single snowflake makes a drift. The drift appears when countless flakes land and stay. In the same way countless grains can build pebbles, pebbles can build larger bodies. A small unlock follows from that simplicity. Planet formation is less like a rare event and more like a slow statistical trend. It depends on how many chances particles get to meet. The second core concept appears as accretion. Accretion is growth by gathering material through collisions and gravity. In plain language, small becomes larger by repeated sticking and by gentle attraction. The disk provides both. It keeps material nearby in orbit. It also supplies a gradient. Inner regions are warmer, outer regions are colder. That gradient is not a detail. It sets chemistry and stickiness. A third visual anchor settles on the inner disk where heat smooths some icy coatings away. The dust there can be more bare. The outer disk looks slightly brighter in scattered light with icy grains reflecting more softly. Another small unlock forms in the boundary between these regions. In many disks, there is a zone where water can freeze into ice on grains. That line is not a drawn circle, it is a band with thickness, it is a transition with a temperature gradient. Ice makes grains more sticky and more massive. That can accelerate growth beyond the line. The disk becomes a place where geography is made of temperature. A gentle scale shift follows. The thickness of the disk can be small compared to its width. The mid-plane layer can be thinner still, yet the disk can extend far beyond the distance where a temperate planet might later orbit. In that wide span, the same rules apply. Orbits remain nearly circular when the disk stays calm. Clumps grow when collisions do not shatter them. As clumps become larger, gravity begins to matter more than surface forces. Bodies start to tug on nearby particles. They sweep paths. They carve gaps. A fourth visual anchor appears as a clean ring where dust density drops. The ring's inner edge looks crisp. The outer edge fades. Such rings can be shaped by growing worlds. They can also be shaped by waves and pressure bumps in the gas. Either way, they are evidence of structure in motion. Another small unlock appears here. Rings imply that planet formation does not require perfect smoothness. It can be helped by traps and piles. A mild bump in pressure can hold dust like a shallow basin holds water. Particles drift inward due to drag, then slow where pressure changes. That pileup raises collision rates. Growth becomes easier. A second everyday analogy fits the trap without human objects. A quiet bay gathers floating leaves. A strong current in open water spreads them out. The bay concentrates them, in the same way a pressure bump concentrates dust. The concentration matters because it can bridge a difficult stage in growth where pebbles might otherwise spiral inward and vanish. One primary number enters with care. Many gas-rich disks last only a few million years before thinning and dispersing. That is brief compared with the age of a typical star. It is like a short season within a long climate cycle. The number matters because it sets a deadline. Planet building must begin while gas still shapes the disk. Gas provides drag and pressure. Gas also damps violent motion. When gas leaves, collisions can become harsher. A quiet payoff follows. If worlds form efficiently in this short window, then the process may not be delicate. It may be robust. That strengthens the idea that planets should be common across galaxies wherever stars form with disks. A limit of intuition arrives softly. It can be tempting to picture planet formation as a neat assembly line. Reality is messier. Growth can stall, collisions can grind bodies into dust. Orbits can be stirred by nearby companions. Disks can fragment or warp. Yet the outcome still often includes planets, even if sizes and arrangements vary. The limit of observation follows and becomes specific. In distant galaxies, individual disks are too small and too faint to be separated from the blended light of billions of stars. A single ring around one young star is lost inside a galaxy's glow. Evidence must be indirect. It comes from understanding the physics of disks nearby and applying that understanding broadly. It comes from seeing that disks appear wherever stars are born and starbirth occurs in many galaxies. The boundary is not philosophical, it is about resolution and contrast. Small structures vanish at great distance. Large trends remain visible. Another visual anchor arrives in a star-forming region inside a distant galaxy. It is a knot of blue light surrounded by darker dust. The knot is not a single star. It is a crowd of young stars embedded in cloud remnants. In such regions, disks must be numerous. Most are unseen as individuals. Their combined effect still matters. Dust absorbs some light and re-radiates it at longer wavelengths. Gas cools and flows. Material cycles. This reinforces another quiet unlock. Planet formation is not a rare add-on to star formation. It is one of the natural paths that leftover material takes when rotation is present. If this path is common, then the universe supplies worlds in vast numbers, even if only a fraction become habitable. The section's calm conclusion settles into the disk's fading edges. A world begins as an imbalance. It begins as a slight excess of dust in one place. It grows by repeating the same small steps until gravity dominates. Nothing in this chain relies on a special galaxy. It relies on general behavior of matter. The next step moves from disks to composition. Some galaxies provide more heavy elements than others. That difference can tilt the odds toward rocky planets and complex chemistry, and it becomes the next quiet layer in the probability story. A galaxy shows itself as a layered glow. A warm central bulge looks smooth and dense. The outer disk looks mottled with blue knots set among darker dust lanes. The early point is quiet and firm. The chance for rocky worlds rises when a galaxy carries more heavy elements. Those elements are not rare miracles. They are the slow ash of earlier generations of stars. In the spiral arms, starlight filters through dust in thin sheets. The dust is not a decoration. It is a record of what the galaxy has already made. A small unlock appears in that record. Rocks require more than hydrogen and helium. Carbon, oxygen, silicon, iron, and other heavier atoms must be present. Without them, solid grains remain scarce. Planets can still form, but the inventory for hard surfaces becomes limited. The galaxy's darker lanes become a map of solids. A second anchor comes from colour. Blue knots mark regions where new stars burn hot and briefly. Redder light marks older populations that shine more gently. The contrast is a chemical story told through time. Young stars form from gas that has been processed before. Old stars formed when the gas was simpler. A soft scale shift appears. The difference between a single atom and a spiral arm is enormous. Yet the spiral arm is built from atoms repeating the same rules of bonding and cooling. The first core concept arrives as metallicity. Metallicity is the fraction of elements heavier than helium. In plain language, it measures how enriched the gas has become. A natural analogy fits without human scenes. After repeated volcanic seasons, soil can hold more minerals. The landscape does not change its physics. The variety of available compounds increases. In the same way enriched gas holds more ways to build solids. That matters because solids are the seeds of rocky planets. A first visual anchor settles on the boundary between a dusty arm and a clearer gap. The arm has thicker curtains. The gap has thinner haze. Along that boundary, dust grains scatter light and create a soft edge. Those grains are where planet building begins. They can clump, they can coat with ice, they can drift into disks around young stars. A small payoff follows. Higher metallicity often means more dust. More dust means more surfaces. More surfaces mean more opportunities for complex chemistry and for growth into larger bodies. This is not a guarantee of life. It's a tilt in the odds toward environments with solid ground and long-lived reservoirs. The second core concept is chemical enrichment. Chemical enrichment is the rise of heavy elements over time. Stars create heavier atoms. Stellar winds and explosions spread them outward. Gas mixes and returns to form new stars. Over long spans, the galaxy becomes less primitive. The imagery shifts to a quiet region of the disk where gas is thin. Here the light looks clean. In the dense arm it looks muted. The difference is not only density, it reflects how much solid material sits in the line of sight. Dust absorbs and reddens light. Dust also cools gas by radiating energy away. Cooling matters because cooler gas collapses more easily into new stars and disks. Another small unlock appears. Metals do not only build rocks, metals also help gas shed heat. That can shape where stars form and how efficiently disks appear. A third visual anchor appears inside a star-forming knot. The knot is not a point. It is textured. Bright spots sit inside darker filaments. Within those filaments, tiny grains move like suspended powder in still air. This powder is the raw material for planets. A single number enters with care. In many galaxies, a few billion years can be enough to raise metallicity substantially above the earliest level. This span is long compared with a disk's brief life. It is short compared with the age of a galaxy. It is like a slow coastline changing shape across many tides. The number matters because it opens a simple possibility. Some galaxies begin enriching early. Some sustain enrichment for long periods. That creates long windows where rocky worlds can form repeatedly. A fourth visual anchor settles on an older elliptical galaxy. Its light looks smooth with few obvious dust lanes. The stars are older. The gas is sparse. In such a system, enrichment may be high, yet new star formation can be low. This reveals a quiet complication. Metals alone do not make habitable worlds. Star formation history matters. A galaxy can be enriched and still produce fewer new planetary systems today. A galaxy can be less enriched and still build many stars if gas is abundant. The probability question becomes layered. Metallicity supports solids. Star formation provides fresh disks. Time provides stability. Another payoff appears in the balance of these layers. The most favourable conditions for many rocky worlds can occur in galaxies that both enrich and continue forming stars for long spans. Spiral galaxies often show that combination. They keep cold gas in a disk. They keep forming stars in patches. They keep cycling material through dust and clouds. A limit of intuition arrives softly. It is tempting to imagine that more metals always means better. Reality is more nuanced. Very high metal content can increase dust opacity. That can change how radiation moves through clouds. It can alter heating and cooling. It can shift where planets form within disks. It can also increase the chance of giant planets forming early, which can disturb smaller rocky worlds. The direction of the effect can vary. The trend remains useful, but it is not a simple ladder. A limit of observation follows and stays specific. Metallicity in other galaxies is often measured from integrated light. Spectral lines reveal averages across large regions. Fine gradients within a spiral arm can be missed. Small pockets of enriched gas can hide inside a broader mean. This is a boundary of resolution. It limits certainty about any one system. It does not erase the overall pattern that enrichment occurs widely and repeatedly. Another visual anchor returns to a spiral arm seen edge-on. The dust lane becomes a narrow, dark ribbon. Above it, the starlight looks cleaner. Below it, it looks dimmer and redder. The ribbon shows layering. It shows that solids settle toward the disk mid-plane. That settling is a quiet preparation for planet formation. A scale shift deepens the feeling. A dust grain is smaller than a cell. A disk is larger than a star system. A galaxy is larger than the disk by a vast margin. Across these scales, solids keep appearing wherever metals exist and gas cools. Another small payoff arrives. Because enrichment is common across galaxies, rocky planet formation is not restricted to one neighbourhood. Some galaxies may even reach favourable inventories earlier than the Milky Way. This does not prove that life begins there. It suggests that the physical preconditions for Earth-like surfaces and long chemical histories can arise in many places. The section settles into a calm conclusion. Metallicity is not a magic ingredient. It is a measure of how many building blocks are available for rocks and complex molecules. Chemical enrichment is not a single event. It is a slow accumulation shaped by stellar life cycles and mixing. Together they make a simple statement about plausibility. The universe does not keep heavy elements locked away. It spreads them. It reuses them. In the next step, those elements enter the coldest clouds where organic molecules form in the dark and drift toward the worlds that may one day hold stable seas. A cold molecular cloud hangs in a spiral arm as a dark silhouette against a crowded background of starlight. The early point rests gently in place. Complex organic chemistry can begin in deep space long before a planet forms. The cloud is not uniform. It has layered curtains. Some regions are thin and faint. Some are dense enough to block light almost completely. Along the edges, starlight grazes the cloud and fades into a soft gradient. Deeper inside, darkness grows thicker. Dust grains float through that darkness like fine ash in still air. Each grain carries a surface where atoms can meet and remain together. A first small unlock appears in the roll of the grain. In open space, two atoms can collide and separate. On a surface, separation is less likely. A surface turns brief contact into a lasting pairing. That matters because the earlier steps toward complexity often require many small additions that would otherwise scatter. The visual anchor tightens to a single grain. It is irregular. It has tiny ridges and pits. In the deepest cold, a thin mantle of ice collects over it. The mantle is not smooth, it grows in layers. Water ice forms. Carbon monoxide freezes. Methanol can appear. Simple compounds become a quiet coating that stores material. The primary number enters here with care. The cold interior can hover at about 10 degrees above absolute zero. That is colder than any winter night on Earth. In that cold, motion slows. Atoms stick more easily. Layers last longer. A second small unlock follows from that stillness. Cold does not stop chemistry. Cold can preserve chemistry long enough for new steps to accumulate. The first core concept arrives as a molecular cloud. A molecular cloud is a cold, dense region where molecules survive and form. The definition ends quickly. In plain language, it is a place where gas becomes a sheltered reservoir instead of a fast-moving haze. The everyday analogy becomes a sheltered tide pool. In open surf, patterns break apart quickly. In a protected pool, small structures persist and build. In the same way, a dense cloud allows chemical structures to persist. The physical details keep the scene grounded. The cloud has filaments that twist and branch. It has cores that are denser than their surroundings. It has a faint sheen at the edges where light scatters off dust. A second visual anchor appears at that edge. Ultraviolet light from nearby stars strikes the surface layers. The light does not travel far. It is absorbed and scattered. It creates a thin, active skin on the cloud while the interior remains quiet and cold. Another small payoff appears in that contrast. The edge creates reactive fragments. The interior stores them. Chemistry can alternate between brief activation and long preservation. The second core concept takes shape as ice mantle chemistry. Ice mantle chemistry is reactions that occur within and on frozen layers. The definition stays short. The plain language returns. Atoms land on ice and become trapped. Light and energetic particles can break bonds. Fragments can recombine into new forms. The ice is both a cage and a workshop. The concrete detail matters. The mantle is layered. It can trap bubbles. It can form porous regions where small molecules sit in pockets. Those pockets allow repeated encounters which favours complexity. A third visual anchor settles into the interior core. The starlight fades to almost nothing. A faint infrared glow still leaks through in some wavelengths. Most visible light is gone. In this interior, cosmic rays pass through. Cosmic rays are high-energy particles that can penetrate dense regions. 2 sentences keep it plain. They carry energy into the cold where starlight cannot reach. They can trigger chemical change without warming the whole cloud. 1 sentence closes why it matters. Even deep interiors can remain chemically active over long time. A soft scale shift stretches the scene. A single grain is far smaller than a cell. A dense core can be large enough to form many star systems. A spiral arm contains countless such cores. The same layered process repeats across that span. Ice collects, light processes the edges. Particles carry energy inward. Complexity grows in small increments. Another payoff lands. Organic molecules do not require a planet to begin. They can form as part of the general cycle of matter in a galaxy. This changes the probability story. If complex molecules are widespread, then new planets do not start from a blank chemical slate. They inherit a chemical head start. The scene shifts to motion within the cloud. Filaments flow slowly toward denser nodes. The density increases toward a core. The core becomes slightly warmer as it contracts. The outer layers remain cold. This creates a gradient in temperature and pressure. The gradient shapes where different ices remain stable. A fourth visual anchor appears as a contracting core with a faint hourglass shape in its density profile. Material funnels inward. The outer envelope remains diffuse and irregular. Inside the core grows smoother and more compact. Another small unlock arrives here. The same collapse that makes stars can also carry organics into the environments where planets will form. As the core contracts, a disk can appear around a young star. The disk inherits icy grains. It inherits carbon-rich coatings. The chemistry does not need to restart. It transitions. A limit of intuition arrives softly. It can feel counterintuitive that the coldest, darkest places can be chemically productive. Intuition expects warmth to be required for complexity. In these environments, time replaces heat. A reaction that is slow can still occur if it is allowed to repeat over long spans. A specific limit of observation follows. Many molecules reveal themselves through narrow spectral fingerprints. Those fingerprints can be faint. In distant galaxies, the fingerprints can blur into noise because the light is weak and the sources overlap. The boundary is clear. Chemical richness can be inferred in broad strokes, but it is difficult to map molecule by molecule across intergalactic distances. The uncertainty is not about whether chemistry can happen. It is about how precisely it can be measured in remote systems. A fifth visual anchor returns to the edge of a cloud where a nearby star cluster lights the surface. The surface looks like a carved relief. Bright rims outline darker cavities. Scattered light forms a soft halo. In those rims, photochemistry can create reactive species. In the shadowed cavities, the products can settle onto ice. Another payoff follows. The interplay of light and shadow creates a natural rhythm of activation and storage. This rhythm can produce a range of organics from simple chains to more complex rings. The language stays cautious. Not every molecule leads to life. Not every environment preserves what it makes, yet the larger statement remains stable. Organic chemistry is not an exotic exception. It appears as a normal consequence of carbon-cold surfaces and energy sources that reach even the dark. The section settles into a calm conclusion. Molecular clouds act as slow chemical reservoirs. Ice mantles act as quiet surfaces where complexity can accumulate. Energetic particles and faint light provide intermittent activation. Together, these processes prepare material that later enters disks and planets. The next step turns toward energy stability on a formed world where chemistry can persist in liquid environments and move from complex molecules towards self-sustaining systems. A quiet star shines with a steady output, and a small rocky world circles at a distance where heat neither bakes nor freezes the surface for long. The early point settles without drama. Life's chances rise when energy arrives steadily for a long time. The scene holds a physical detail that stays simple. A thin line separates day from night across the planet's curve. Along that terminator, clouds form a soft band. In the sunlit, half-scattered light brightens the upper air. In the dark half, the glow fades into deep shadow. A small unlock appears in that boundary. Chemistry needs contrast. It needs gentle gradients of temperature and light. Too much variability can erase slow progress. Too little variability can stall cycles. A planet that rotates and orbits creates repeating patterns. Warm regions cool, cool regions warm. Water can circulate if it exists. Gases can mix. Over long time, repetition becomes a kind of stability. The first core concept takes shape as energy stability. Energy stability is a long period of relatively steady power input. The definition stays short. In plain language, it means fewer violent swings that sterilize surfaces or strip atmospheres. A visual anchor sharpens on the star's surface. Bright patches drift and fade. Darker regions appear and dissolve. The overall light remains calm even as small patterns ripple across it. That calm matters because chemical networks are fragile in their early stages. A molecule that forms slowly can be destroyed quickly by harsh bursts. Stability does not guarantee biology, but it allows chemistry to keep its gains. The everyday analogy stays natural. A steady tide along a rocky shore reshapes the boundary without sudden floods. The same motion returns again and again. Over time, small changes accumulate. In the same way, steady energy allows small chemical steps to persist and build. A second small unlock appears when scale shifts from the star to the orbit. The star is vast compared with the planet. The planet is a small bead moving through a wide emptiness, Yet the orbit controls the planet's climate more than the star's size does. A small change in distance can mean a large change in surface temperature. This leads into the second core concept as the habitable zone. The habitable zone is a range of distances where liquid water can persist on a surface. The definition ends quickly. 2 sentences return to plain language. It is not a perfect ring. It shifts with atmospheric thickness, cloud cover and reflectivity. 1 sentence closes why it matters. Liquid water is a strong solvent for complex chemistry. The planet's surface provides concrete detail. A darker band near the poles suggests ice. The boundary between ice and darker ground forms a soft curve, not a sharp edge. That curve can drift with seasons. If oceans exist, a faint glint can appear where sunlight reflects at a shallow angle. The glint comes and goes as the planet turns. Another small payoff follows. A cycle of evaporation and condensation can move heat and chemicals across the surface. It can create stable interfaces where chemistry concentrates, such as shorelines and porous rock. Those interfaces are not exotic. They are simple boundaries where gradients gather. The third core concept enters as time, but it stays tied to energy. A stable star can shine for about 10 billion years. That span is longer than the time it takes for mountain ranges to rise and erode many times. The number matters because life on Earth takes a long time to become complex. Simpler life can appear earlier, but chemical organization still needs persistence. A long stellar lifetime provides many chances for a planet to remain wet and temperate. Another visual anchor appears in slow weather. A wide storm band curls along a latitude. The band has a brighter top and a darker underside. It moves gradually. The rotation carries it across the terminator and into night. In darkness, the band cools and thins. In daylight, it thickens again. This repeating pattern offers a quiet unlock. Climate is not a single constant temperature. Climate is a set of recurring flows. If those flows stay within gentle bounds, chemistry can explore many pathways without being reset to zero. A scale shift extends outward. In one region of a galaxy, stars form in clusters. Some are massive and short-lived, some are smaller and longer-lived. The long-lived ones offer extended stability. The short-lived ones burn bright but end quickly. This difference changes the odds for biology. A planet needs more than a brief warm interval. It needs a long quiet window. The planet also needs protection. A thin atmosphere can be lost. A magnetic field can help, but it is not the only factor. Gravity matters, distance matters, stellar activity matters. Another small payoff appears as these factors combine. Stability is not a single switch. It is a balance of many gentle protections that keep water from boiling away or freezing forever. A limit of intuition arrives softly. It can be tempting to imagine the habitable zone as a simple band where life either is possible or is not. Real worlds are more complicated. A thick atmosphere can warm a world far from its star. Bright clouds can cool a world closer in. A reflective ice cover can trap a planet in deep freeze. A dark ocean can absorb heat and prevent it. The boundary is fuzzy because feedback loops can amplify small differences. The limit is not only conceptual, it is physical. Small shifts in reflectivity can move a planet into a new climate state. A specific limit of observation follows. Even in nearby star systems, the surface of a small rocky planet is hard to characterize. At intergalactic distances, individual planets are lost in the combined light of billions of stars. A single ocean glint cannot be separated. A single seasonal change cannot be tracked. Evidence must come indirectly through general physical reasoning, and through patterns in atmospheric light where those patterns can be measured. That boundary is about faint signals and overwhelming background. It limits certainty about any one distant world. It does not remove the broader conclusion that stable stars and temperate orbits can exist in many galaxies. Another visual anchor holds on the planet's atmospheric rim. The rim is a thin shell that brightens when seen at a grazing angle. It shows layering. A higher haze scatters light softly. Lower clouds form thicker patches. This shell is where energy becomes chemistry. Sunlight enters, heat circulates, gases react. If life exists, this shell can also carry its traces. A final small payoff settles. The most accessible signs of biology may not be bodies or oceans. They may be atmospheric imbalances that persist over time. The section closes gently. Stable energy creates long windows. Habitable distances create temperate surfaces. Time allows chemistry to accumulate and explore. The next step moves into the atmosphere itself, where certain combinations of gases can suggest ongoing processes that resemble biology. A rocky planet shows a thin atmospheric rim as it crosses the face of its star, and the rim glows briefly like a pale ring before fading back into darkness. The early idea arrives calmly. If life exists, it can leave chemical patterns that are easier to notice than any organism. The planet's air is not a single layer. It is stacked. Lower layers hold thicker gases and aerosols. Higher layers thin into a faint haze that scatters light and softens edges. Along the terminator, day meets night in a narrow band. Temperature changes across that band. Condensation can begin there. Thin cloud decks can form a curved seam. That seam matters because boundaries concentrate chemistry. A small unlock appears in the way light behaves at grazing angle. When starlight passes through the rim, some colours are absorbed more than others. The result is not a picture of continents. It is a set of tiny missing slices in the light. Each missing slice can point to a specific molecule. This is the doorway to the idea of a biosignature. A biosignature is a measurable sign that can be produced by life. The definition ends quickly, then plain language returns. It is not a single magic gas. It is a pattern that is hard to sustain without ongoing renewal. The first visual anchor deepens. The atmospheric rim looks thicker near the planet's equator. It looks thinner near the poles. The brightness is uneven because cloud tops and hazes scatter light differently. This unevenness becomes the first caution. Atmospheres are messy. They hide their own composition behind layers. Another small payoff follows. Even a messy atmosphere can reveal certain molecules because absorption happens at specific colours regardless of clouds. Yet clouds can mute the depth of those notches and blur their edges. The second core concept arrives as chemical disequilibrium. Chemical disequilibrium is a persistent mixture that should react away without renewal. In plain language, some gases do not like to coexist for long. If they remain together, something must keep producing them. On Earth, oxygen and methane form a famous example. Oxygen tends to destroy methane. Methane tends to consume oxygen. Their long coexistence points to constant sources. The analogy stays natural and avoids human scenes. Two currents meet in a tidal estuary. One is fresh and one is salty. The boundary stays sharp only while flow continues. If flow stops, the boundary fades and mixes away. In the same way, a sharp chemical imbalance can persist only while sources keep it alive. This matters because it turns the search for life into a search for maintenance. Life is one kind of maintenance system. Geology can be another. Sunlight can drive another. The rim glows again as the transit continues. The ring is thin. The signals within it are thinner still. Another small unlock appears in scale. A biosignature does not need to be abundant to be detectable. It needs to have a strong absorption fingerprint and a long enough atmospheric path. Yet abundance still matters for certainty. One primary number enters with care. Some key atmospheric gases can exist at levels of 1 part in a million and still influence light in measurable ways under ideal conditions. 1 part in a million is like a single pale pebble among a million darker stones in a riverbed. It is small, but it can stand out if the contrast is right. This number matters because it shows both promise and fragility. It is possible for a tiny fraction to matter. It is also easy for noise to imitate it. A new visual anchor settles on the planet's night side, where faint air glow can appear as a thin line caused by atoms and molecules relaxing after absorbing energy. The glow is subtle. It varies with latitude. It can shift with storms. This introduces another gentle idea. Not all biosignatures are about life directly. Some are about the state of the atmosphere and the energy flows inside it. Strong photochemistry can create oxygen without life in certain contexts. Volcanism can create methane without life in certain contexts. The third core concept enters as false positives and it stays grounded. A false positive is a lifelike signal produced without life. The definition stays short. 2 sentences return to plain language. A planet can lose water and build oxygen through sunlight breaking vapor, then hydrogen escaping. A planet can release methane through reactions in hot rock deep below the surface. 1 sentence closes why it matters. A single gas rarely settles the question. The pattern and the context matter. A small payoff follows as context becomes visible in the same light. The star's type matters because its ultraviolet output shapes photochemistry. The planet's gravity matters because it controls escape. The presence of water vapor matters because it links oxygen to an active water cycle. The presence of carbon dioxide matters because it can buffer climate and alter chemistry. The planet's temperature structure matters because it sets where clouds form and where absorption happens. The physical details stay close. Cloud layers can form a bright cap that reflects light. Hazes can form a diffuse veil that blurs features. Temperature inversions can trap gases in specific layers. In that layered shell, chemistry is not evenly mixed. It is stratified. Another visual anchor settles on a thin haze layer, like smoke spread in a smooth sheet that increases scattering and makes the rim look slightly larger. This haze can hide lower layers. It can also carry its own chemistry. Another small unlock appears. A strong haze can mimic the muted signatures of certain gases, making an atmosphere seem simpler than it is. Yet haze can also be a product of complex organic reactions under sunlight. The same feature can complicate and enrich interpretation at once. A limit of intuition arrives softly. It is tempting to think that life must announce itself with a clear and unique chemical stamp. Reality is quieter. Many processes can produce similar gases. Many atmospheres can be confusing mixtures. Some life could also remain hidden. Microbial ecosystems can thrive without producing strong global signatures. Life can also exist under ice or rock with minimal atmospheric effect. The absence of a biosignature is not proof of absence. It is only a statement about detectability. A specific limit of observation follows and stays practical. The atmospheric ring is thin compared with the star's disk. Its contribution to the total light is tiny. Small changes in cloud cover can alter the signal more than small changes in composition. At great distance, many stars blend into one glow. In another galaxy, that blend becomes overwhelming. The light from one planet is drowned. Even if a perfect biosignature exists, it becomes nearly impossible to isolate it from the combined glare of billions of suns. This boundary is about contrast and resolution. It does not forbid life, it forbids easy measurement from far away. Another small payoff lands in how science still moves forward. If direct detection in other galaxies is nearly unreachable, the probability question leans on what is measurable. Chemistry is universal. Planet formation appears common. Stable stars exist in many environments. Biosignature logic can be tested nearby and then used as a framework for expectation at larger scales. The rim fades as the transit ends. The planet becomes a dark point again. The final transition stays gentle. The next step turns toward how light from entire galaxies is analysed as a blended signal, and how that blending sets the strongest limits on what can be inferred about life beyond the Milky Way. A distant galaxy appears as a single soft oval of light with no stars resolved and no planets visible. The early point rests in place. At intergalactic distance, the universe hides details and reveals only averages. The galaxy's glow looks smooth, yet it is made of countless sources layered along the line of sight. Dust dims some wavelengths. Hot young stars brighten others. Older stars add a redder background. The light carries information, but it is compressed into a blended spectrum. A first visual anchor settles on that spectrum as a quiet ribbon. Across the ribbon, tiny notches appear where specific wavelengths are missing. Those notches are narrow. Their edges can be rounded by motion and by the mixing of many sources. A small unlock appears in what a notch can still tell. Even when individual objects are lost, atoms and molecules leave fingerprints. The question becomes what scale those fingerprints refer to. In a nearby star system, a notch might come from one atmosphere. In a distant galaxy, a notch usually comes from gas spread across large regions. The first core concept arrives as integrated light. Integrated light is the combined light of many unresolved sources. The definition ends quickly. In plain language, it is what remains when distance turns a crowd into a single glow. The analogy stays natural. A foggy valley hides individual trees. Only the colour and brightness of the whole hillside remain. From that, the presence of dense forest can be inferred, but not the shape of a single leaf. In the same way, integrated light can reveal broad chemical content, but not a single planet's biosphere. A second visual anchor appears as a bright point behind the galaxy like a distant beacon. Its light passes through the galaxy's outer halo and disk. Along that path, certain wavelengths are absorbed. The pattern depends on what atoms lie in the way. This introduces the second core concept as absorption spectroscopy. Absorption spectroscopy is reading missing colours to identify intervening matter. The definition stays short. 2 sentences return to plain language. A specific element removes specific colours. A specific molecule removes a different pattern of colours. One sentence closes why it matters. Chemistry can be detected even when matter does not glow brightly. A small payoff follows. Absorption lines allow mapping of gas in halos, filaments and outer disks. They reveal carbon, oxygen and other elements beyond the bright stars. They confirm that life's raw materials exist widely, yet they also show the boundary. The absorption usually measures a long column through space. It averages over many environments. It cannot isolate a thin atmospheric ring around a single world. The physical detail stays concrete. The line shapes can broaden because gas is moving. Some gas moves towards the observer, some moves away. Their velocities smear the notch into a wider dip. The dip's width carries motion information, but it also blurs fine structure. Another small unlock appears in this blur. Motion is both a clue and a complication. A galaxy rotates. Gas flows in and out. Stellar winds push material. All of that motion broadens features. The spectrum becomes a summary rather than a photograph. A gentle scale shift follows. A planet's atmosphere is a shell a few tens of kilometers thick. A galaxy's gas disk can be thousands of light years thick in its diffuse components. The path length difference is immense. Yet the atmosphere's signal is tiny because its area is tiny compared with the galaxy's light. The imbalance of scale explains the detection problem without drama. One primary number enters carefully. A bright spiral galaxy can contain on the order of 100 billion stars. That is like counting every grain in a wide stretch of sand and finding that each grain is its own lamp. Against that many lamps, one planet's reflected light is effectively invisible. The number matters because it makes the contrast problem intuitive. Even if a planet emits or reflects a distinctive signature, the signal is diluted by countless unrelated photons. A third visual anchor appears as a faint dust lane crossing the galaxy's centre. The lane creates a sharp contrast edge against the bulge's smooth glow. It shows that dust can block and redden light. That matters for life inference because dust can mimic some effects of atmospheric composition at a large scale. Dust can hide young stars. Dust can also change the apparent ratios of chemical lines by absorbing certain wavelengths more strongly. Another small payoff follows. To interpret a spectrum, models must include dust star populations and gas conditions. The life question sits on top of that complexity, not separate from it. A limit of intuition arrives softly. Intuition expects that a strong biosignature would stand out anywhere. Integrated light breaks that expectation. A biosignature is not only about chemistry, it is about isolation. Without isolation, signals blend. Another limit of observation follows and stays specific. Telescopes collect a finite number of photons. For a distant galaxy, many photons are needed to measure small notches with confidence. The atmosphere adds noise for ground observations. Instruments add noise in all cases. Even in space, the detectors have limits. To detect a subtle pattern, the exposure must be long and the light must be bright. For planets in other galaxies, the light is both faint and swamped. This boundary is not about cleverness. It is about photon statistics and contrast ratios. Another visual anchor shifts to a gravitational lens where a distant galaxy's light is stretched into an arc by the gravity of a foreground mass. The arc looks like a curved smear with brighter knots. The knots are magnified regions. This introduces a cautious possibility. Lensing can boost brightness and stretch images. It can in rare cases allow more detailed study of distant galaxies than would otherwise be possible. Another small unlock appears. Even with lensing, what is magnified is usually the galaxy's bulk light, not a single planet. Lensing helps study star formation and gas. It does not easily isolate biosignatures from individual worlds. The lens becomes a reminder that nature sometimes offers amplification, but not necessarily the kind needed for life detection across intergalactic space. The section's calm conclusion settles. The universe provides chemical evidence at large scale. It provides models that can estimate how common planets and stable environments should be. It does not yet provide direct biosignature measurements from planets in other galaxies. The probability discussion therefore rests on universal processes, and on the vast number of opportunities while acknowledging the strict observational barrier created by distance and blending. The transition stays soft. The next step turns toward time itself, because distant galaxies are seen in earlier stages, and that time view changes what can be said about when life could have begun elsewhere. A field of faint galaxies fills the darkness, each one a soft smudge with slightly different colour and shape. The early point arrives quietly. Looking far away means looking back in time, so the search for life becomes entangled with the universe's history. The light from a distant galaxy begins its journey long before the present moment. By the time it arrives, the galaxy may have changed, stars may have aged, gas may have moved, new systems may have formed. The image on the sky is real, but it is a record of an earlier chapter. A first visual anchor settles on a distant spiral that looks less crisp than nearby ones. Its arms are faint, its centre is compact. Dust lanes are subtle. The galaxy's light is shifted toward redder wavelengths because space expands. The edges are softened not because the galaxy is hazy, but because distance compresses details. A small unlock appears in this compression. Even if planets and life exist there now, the view shows conditions from long ago. That does not make the view useless. It changes what the view can support. It supports questions about how quickly galaxies enrich, how long stars form, and how stable environments might persist. The first core concept arrives as look-back time. Look-back time is the time light spends travelling to the observer. The definition ends quickly. 2 sentences return to plain language. A galaxy seen far away is seen as it was. The farther the galaxy, the earlier the snapshot. 1 sentence closes why it matters. The probability of life depends on when ingredients and stable habitats become available. A second visual anchor appears in a distant galaxy's starlight dominated by blue regions that suggest intense star formation. The light looks patchy. Bright knots cluster along a faint disk. The gas in such galaxies can be turbulent. Radiation can be stronger. Explosions can be frequent. These conditions can challenge fragile atmospheres. Another small payoff follows. Early in cosmic history, galaxies can be chemically poorer and more energetic at the same time. That combination can reduce the fraction of calm, metal-rich, long-lived planetary systems, yet it does not eliminate them. It suggests that life's best windows may open later in a galaxy's evolution after enrichment and after star formation becomes less extreme. The second core concept arrives as cosmic chemical evolution. Cosmic chemical evolution is the rise of heavy elements over cosmic time. The definition stays short. In plain language, the universe begins simple and becomes more chemically varied as stars process material. A gentle analogy fits. A river begins near a spring with clear water. Downstream, it picks up minerals from many rocks. The water becomes richer in dissolved material. The river is still water. It simply carries more variety. In the same way, later galaxies carry more chemical options for solids and complex molecules. One primary number enters with care. The universe is about 13 billion years old. That span is like a long geological era compared with any single planet's history. The number matters because it frames opportunity. There is time for many generations of stars. There is time for enrichment to spread. There is time for stable stars to shine for billions of years. There is also time for life to appear, persist, and vanish in places that may never be observed directly. A third visual anchor settles on an old galaxy with a smoother glow. Its colour is redder, suggesting older stars. Star formation is quieter. The disk, if present, is faint. In such a system, radiation bursts can be rarer. That calm can favour long-term stability for planets that already exist. Another small unlock appears. The best conditions for life are not only about having many young stars. They can also be about having enough calm time after formation when atmospheres and oceans can stabilise. Time is not merely duration. Time is a filter. It allows unstable systems to fail and stable ones to persist. This introduces a subtle point. A galaxy that has existed longer has had more chances to produce habitable worlds, but it has also had more time for those worlds to be altered or destroyed. The net effect depends on balance. The physical details remain gentle. In a galaxy's disk, spiral density waves can continue sweeping gas into star-forming regions. In a calmer galaxy, those waves can fade, gas can thin, the supply of new stars can slow, yet existing planetary systems remain. Another payoff follows. A slower galaxy can still host life if life arises on older worlds. The probability does not depend solely on current star birth. It depends on the accumulated inventory of stable worlds and the time they have been stable. A limit of intuition arrives softly. Intuition treats time as a simple line. Look-back time makes time layered. The present view contains many past moments at once because different galaxies sit at different distances. The sky becomes a mosaic of eras. This complicates any attempt to claim a single cosmic moment that is best for life. The best moment can vary by environment. A specific limit of observation follows. From far away, it is hard to measure a galaxy's precise age distribution of stars. Models infer it from colours and spectral features. Dust can mimic age by reddening light. Bursts of recent star formation can hide a large older population. The boundary is specific. Age estimates carry uncertainties that grow with distance and with blending. Yet broad trends remain. Galaxies generally enrich over time. Many galaxies have older stars and stable, long-lived stars. Some galaxies have had billions of years more than the Milky Way's sun to host steady planetary climates. Another visual anchor appears in a globular-like concentration around a galaxy, a dense halo region of old stars. The stars are packed tightly, their light is warm and steady. Such environments can be old. They can be chemically varied depending on history. They can also be dynamically crowded, which can disturb planetary orbits. This anchor foreshadows a later nuance. Age alone is not enough. Crowding can matter. Radiation environment can matter. Metallicity can matter. The life probability question becomes a set of overlapping windows rather than one door. Another small payoff lands as the time perspective widens. It becomes plausible that life could have arisen elsewhere long before Earth existed. It also becomes plausible that such life could have ended long ago. The absence of a current detectable signal would not disprove its past existence. In that sense, the universe can be biologically active across time, without leaving clear persistent signs at intergalactic distance. The section closes gently. Look-back time turns distant galaxies into historical records. Cosmic chemical evolution suggests that richer chemistry becomes more common as time passes. Long-lived stars provide long, steady windows. Together, these points make life beyond the Milky Way more plausible but also more hidden behind the layered view of time. The next step moves into environments that can be especially harsh, such as intense galactic centers where radiation and density can raise barriers to habitability, even when chemistry is rich. Near a bright galactic center, light thickens into a dense glow, and the surrounding regions show sharp gradients from brilliant to dim. The early point arrives with calm precision. Rich chemistry does not always mean gentle conditions because some environments can be too energetic for stable atmospheres and long-lived surface water. The center is not a single point. It is layered. A smooth bulge of older stars surrounds a more compact inner region. Dusty filaments thread through it. Bright knots flare where gas compresses. The physical details are clear. Edges are sharp in brightness, shadows are deep behind dust. Radiation fields change quickly over short distances. A first small unlock appears in the meaning of that gradient. Habitability is not only about having an ingredients, it is also about not being constantly strip-baked or sterilized. Near the center, high-energy light can break molecules apart. Dense star populations can increase the frequency of energetic events. Gas flows can be turbulent. All of this can make stability harder. The first core concept arrives as radiation environment. Radiation environment is the level and type of energetic light and particles in a region. The definition ends quickly. 2 sentences return to plain language. High-energy radiation can break chemical bonds and heat upper atmospheres. Repeated exposure can drive atmospheric escape. 1 sentence closes why it matters. A planet can lose its protective shell and its surface water if energy is too intense. A visual anchor settles on a planet orbiting a star embedded in the inner bulge. The planet's sky would look crowded with bright stars, but the scene stays abstract and non-human. The planet's atmosphere forms a thin shell. If ultraviolet and X-ray light are strong, the upper layers can expand like a heated veil. The boundary between the atmosphere and space becomes less sharp. Particles can leak away more easily. Another small payoff follows. A planet does not need a single catastrophic event to lose habitability. Slow erosion of air can be enough if it persists for long spans. A second visual anchor appears in a nearby supernova remnant, a faint expanding shell with a brighter rim and a darker interior. The shell shows an edge where shock meets surrounding gas. That edge is a concrete physical detail. It marks where energy is deposited into the medium. In a crowded inner region, events like this can occur more often than in quieter outskirts. The second core concept arrives as atmospheric escape. Atmospheric escape is the loss of atmospheric particles into space. The definition stays short. 2 sentences return to plain language. Heated upper air can flow away like a slow wind. Stellar and cosmic particles can also knock molecules into trajectories that never return. 1 sentence closes why it matters. Without a stable atmosphere, surface water and stable temperatures become harder to maintain. 1 primary number enters carefully. In some galactic centers, the density of stars can be thousands of times higher than in calmer disk regions. That is like comparing a sparse field to a thick thicket where points of light cluster close together. The number matters because it changes the frequency of close encounters and the background brightness. More stars nearby can mean more gravitational nudges and more radiation sources in the neighborhood. A small unlock follows. Even if a planet's own star is calm, the surrounding environment can add stress. This leads into a subtle nuance. A harsh region does not remove all possibilities, it reshapes them. Life might be more plausible in sheltered niches. Planets deeper in gravity wells can hold atmospheres more strongly. Worlds with thicker air can resist escape longer. Subsurface habitats can be protected. Yet surface biosignatures become less likely if the atmosphere is thin or constantly changing. Another visual anchor settles on a dusty ring of gas near the center, with a sharp inner edge and a broader outer fade. Gas streams into the ring. Collisions and compression create bursts of star formation. The ring is a conveyor of energy. This anchors another payoff. The same processes that enrich the center with heavy elements can also make the center volatile. Chemistry can be rich, but stability can be scarce. The probability of life becomes a map with gradients rather than a uniform field. A limit of intuition arrives softly. Intuition might assume that the most chemically rich regions are the best. The center challenges that. More energy can mean more disruption. A region that looks favourable on an ingredient list can be unfavourable in stability. The lesson is not pessimism, it is specificity. Habitability depends on multiple overlapping conditions that can trade off. A specific limit of observation follows. From far away, a galaxy's centre can dominate the light. The blended glow can hide the quieter outskirts. Integrated measurements can be biased toward the most luminous regions. This can distort inference about how common calm environments are. The boundary is clear. Without resolving different regions, it is hard to weigh which parts of a galaxy contribute most to long-term habitability. Nearby galaxies can be mapped in more detail. Distant ones cannot. Another small payoff appears in the outskirts themselves. Spiral arms and outer disks often have lower radiation backgrounds. Star formation can be patchy rather than intense. Supernova frequency can be lower, gas can be cooler. These are the conditions that favour stable atmospheres and long-lived surface water, even if metallicity is slightly lower than the centre. The scene shifts outward along a brightness. Brightness is seen gradient. The bulge fades, the disk becomes more structured. Dust lanes appear again, but less concentrated. The environment feels calmer. This quiet movement carries the transition. Life beyond the Milky Way is not only about whether galaxies have the right atoms, it is also about whether galaxies have regions that are calm enough for long chemistry to persist. The next step moves into crowded, stellar environments where gravity rather than radiation becomes the main source of disruption, and where stable orbits can be harder to maintain. A dense stellar cluster hangs like a concentrated spray of light with a bright core and a smoother halo that fades outward. The early point settles quietly. Crowded neighbourhoods can make long-term habitability harder because gravity constantly rearranges orbits. The cluster is not uniform. Star density rises toward the centre in a steep gradient. The inner region looks almost continuous because so many points overlap. Between those points, space still exists. It is simply filled with more gravitational influence than a quiet spiral arm. A first small unlock appears in the meaning of crowding. A single star with planets can be stable for billions of years when nearby stars remain distant. In a crowded cluster, close flybys become more likely. A flyby does not need to collide. A gentle tug at the wrong time can tilt an orbit. It can stretch an orbit into a longer ellipse. It can disturb the spacing between planets and seed future instability. The first visual anchor tightens to the core, where starlight forms a bright central glow. Individual stars blur at the centre into a smooth brightness peak. At the edge of that peak, points separate again. The physical detail matters. The cluster has a core radius where the glow steepens. It has an outer boundary where stars thin into the background. In the core, gravitational pulls overlap like ripples that never fully fade. A second small unlock appears in the difference between chemistry and stability. A cluster can be old. It can contain stars that have been shining for a long time. Yet stable energy alone is not enough if orbits are repeatedly shaken. Habitability is a balance between time available and the ability to keep environments steady. The first core concept arrives as dynamical perturbation. Dynamical perturbation is a change in an orbit caused by external gravity. The definition ends quickly. 2 sentences return to plain language. A passing star can pull a planet slightly off its path. Repeated pulls can accumulate into a large change over long time. 1 sentence closes why it matters. Small orbital changes can shift climate and can trigger cascading instability in planetary systems. A natural analogy fits without human scenes. In a narrow channel filled with drifting ice flows, a single flow can glide smoothly in open water. In the crowd, each flow nudges others and changes their paths. The nudges are small. The paths diverge steadily until the pattern looks completely different. In the same way, close stellar spacing increases the chance of nudges that change planetary architectures. A third visual anchor forms around a single star in the cluster. Dust and gas are scarce in many old clusters, so new disks are less common. Yet planets formed long ago can still remain. Around the star, a thin belt of distant icy bodies can exist like a faint ring. That ring has a soft edge rather than a sharp wall. A passing star can shear that edge. It can scatter small bodies inward. It can also strip material away into interstellar space. Another small payoff arrives. Even if inner rocky planets remain intact, the delivery of comets and impacts can change surface conditions. Too few impacts can limit chemical mixing. Too many can reset surfaces and atmospheres. In a crowded cluster, the impact environment can vary widely over time, because orbits of small bodies can be stirred repeatedly. One primary number enters with care. In the densest cluster cores, the typical distance between neighbouring stars can be about 1/10 of a light year. That is only thousands of times the Earth to Sun distance. The number matters because it turns the crowd into something tangible. A planet system that extends far outward can be vulnerable when another star passes within that scale. Even if the pass is still far, the slow tug can reshape the outer reservoirs that stabilize inner worlds. A fourth visual anchor settles on the outer halo of the cluster where stars are more widely spaced and the glow becomes grainy again. The density gradient becomes a map of risk. In the core, perturbations are frequent. In the outskirts, they are rarer. Another small unlock appears. Habitability in a cluster may not be impossible. It may be more plausible in the calmer outskirts where stable orbits can persist while stellar lifetimes remain long. The second core concept arrives as orbital stability. Orbital stability is the ability of a system to keep predictable orbits over long time. The definition ends quickly. 2 sentences return to plain language. Stable spacing keeps planets from exchanging energy in ways that grow over time. Stable outer reservoirs reduce sudden showers of impacts. One sentence closes why it matters. Life depends on continuity, and continuity depends on orbits that do not wander too far. A quiet scale shift follows. The orbital period of an inner planet is measured in days or years. The drift of a disturbed orbit can take millions of years. The cluster itself evolves over billions of years as stars exchange energy and slowly migrate. These timescales overlap like layered currents. A stable climate can exist for a long span, then be disrupted by a rare encounter. Another payoff lands in that layered timing. Crowded environments tend to produce long, quiet stretches punctuated by occasional reshaping events. That pattern is important because life can survive gradual change more easily than sudden extremes. A close pass can tilt a planet's orbit and change seasons. It can also destabilize multiple planets at once. It can turn predictable cycles into chaotic ones. A limit of intuition arrives softly. It can be tempting to picture clusters as packed spheres, where chaos is immediate and constant. Reality is subtler. Many encounters are distant. Many planetary systems are compact and resilient. Some disturbances affect only the farthest bodies. Others barely register. The boundary is not a simple yes or no. It is a probability distribution shaped by density, relative speeds, and the architecture of each system. A specific limit of observation follows. Detecting planets in dense clusters is difficult because starlight overlaps and signals blend. The background is bright. Individual stars are hard to isolate in the core. Even when planets exist, the methods that rely on precise light changes struggle in the glare of neighbours. This limitation can bias conclusions. A lack of detected planets in cluster cores does not prove an absence. It reflects a measurement boundary created by crowding and confusion. Another visual anchor appears as a faint tidal edge at the cluster's outskirts where stars begin to drift away under the galaxy's larger gravitational field. The edge is not sharp. It is a thinning gradient. This physical detail matters because it shows that clusters are not closed boxes. They leak stars over time. Planetary systems can leave crowded regions and enter a quieter space. Another small payoff arrives. A system formed in a dense environment might later spend most of its existence in calmer surroundings. The early disruptions could prune unstable architectures and leave survivors that are unusually robust. That possibility does not guarantee habitability, but it shows that crowding can reshape odds in complex ways. The section settles into a calm conclusion. Dense clusters can be chemically mature and very old. They can also be dynamically restless. Gravity, not chemistry, becomes the main barrier to long climate continuity. The next step moves from local crowding to the broader question of statistical expectation across many galaxies where large numbers can make rare habitable niches add up to a significant total. A small red star glows with a deep steady light, and a rocky planet circles close enough that one hemisphere stays in daylight while the other remains in long night. The early point is calm and clear. Life's plausibility expands when the definition of a habitable place includes persistence and shelter, not only Earth-like surfaces. The planet's most striking physical feature is a band of twilight along the terminator. Warm air rises on the day side. Cooler air sinks on the night side. Between them, a narrow ring holds gentler temperatures and softer winds. Clouds gather there in layered sheets with brighter tops and darker undersides. A first small unlock appears in that ring. A planet does not need a uniform climate to host stable chemistry. It can host stable gradients instead. In that twilight zone, liquid water can persist even if the day side is dry and the night side is frozen. The second visual anchor moves into the night hemisphere. Ice spreads in a broad cap. The boundary between ice and bare ground is not sharp. It is a slow curve with a mottled edge where seasonal drift can occur. Under the ice, heat from the interior leaks upward. Rock holds warmth longer than the thin air can carry it away. This introduces the first core concept, tidally locked climate. Tidally locked climate is a pattern where one face stays lit and one face stays dark. The definition stays short. 2 sentences return to plain language. The climate becomes organized around a permanent day and a permanent night. The most stable conditions can sit between them. 1 sentence closes why it matters. Stable gradients can concentrate chemistry and protect it from extremes. A gentle analogy fits the geometry. A stream can keep moving beneath a winter ice roof even while the surface appears motionless. Flow and shelter coexist. In the same way, chemistry can keep cycling beneath harsh skies if a boundary provides cover. A second small unlock arrives in the star itself. Small red stars can remain stable for extremely long spans. Many can shine for trillions of years. That is far longer than the current age of the universe. This single number matters because it changes the role of time. A shorter-lived star offers a narrow window. A long-lived star offers repeated chances for chemistry to explore pathways and settle into self-sustaining loops. The third visual anchor returns to the planet's atmosphere, seen as a thin rim that thickens at the terminator where aerosols and clouds collect. The rim is layered. A higher haze scatters light and softens the limb. Lower clouds form denser patches that drift slowly along the boundary. Another small payoff follows from this layering. A thick atmosphere can move heat from day to night and reduce the contrast. It can widen the temperate ring. It can also protect surface water by buffering temperature swings. The second core concept takes shape as resilience. Resilience is the ability to persist and recover under changing conditions. The definition ends quickly. 2 sentences return to plain language. Life on Earth occupies hot vents, frozen deserts, and deep rock pores. Survival is often about steady energy and protection, not comfort. 1 sentence closes why it matters. If biology is resilient, then the set of plausible habitats widens beyond familiar coastlines and mild skies. The next visual anchor shifts below the surface. Porous rock forms a lattice of microcavities filled with thin films of water. Chemical gradients form where different minerals meet. Heat seeps upward in a slow gradient from warmer depths to cooler crust. In that gradient reactions can run continuously, driven by differences in chemistry rather than sunlight. A small unlock appears here. A biosphere can be largely invisible from above if it lives underground or beneath ice. It can metabolize chemical energy and release only faint gases or none that reach the upper air. This directly reshapes expectations about detection. Life can be common and still quiet. The section scale shifts gently again. A cell-scale film in rock pores can persist for years. A subsurface ocean can persist for millions of years. A red star can persist for spans longer than galaxies have existed in their present forms. Across those layers of time and size, the common requirement is continuity of energy and a medium for complex reactions. Another payoff follows. Under that requirement, many worlds that look harsh at the surface can still offer stable niches. The scene returns to the Terminator ring, now seen from higher altitude. The ring appears as a faint belt. On the day side, deserts can form where water evaporates and clouds break. On the night side, frost can accumulate in broad basins. The belt remains the place where evaporation, condensation, and circulation meet. This is a concrete boundary, not a metaphor. It is a region where gradients overlap and where chemistry can concentrate in repeated cycles. A limit of intuition arrives softly. Intuition often treats a planet as either friendly or hostile based on an average temperature. A tidally locked world is not ruled by averages, it is ruled by persistent contrasts. Another limit of intuition follows in the star's behaviour. Red stars can be stable in long terms while still producing flares in shorter terms. Energetic bursts can bathe a close planet in ultraviolet light and charged particles. That can erode atmospheres and break molecules. It can also drive chemistry in upper layers and create hazes. The balance depends on magnetic shielding, atmospheric depth, and the planet's gravity. The difficulty is not that the environment is impossible. The difficulty is that it's conditional. A specific limit of observation follows. Even nearby, distinguishing a hazy atmosphere from a clear one can be hard because of clouds and aerosols blur spectral fingerprints. Flares can change the star's light during a measurement and add noise. The signal from a small rocky planet is tiny compared with the star. At intergalactic distances, the challenge becomes overwhelming because the planet's light is lost inside a galaxy's integrated glow. This boundary is precise. The limitation comes from contrast and photon scarcity, not from a lack of possible habitats. Another visual anchor settles on a frozen night basin with a thin crack network. The cracks form dark lines that spider across pale ice. Beneath them, warmer material can reach the surface in small releases, then refreeze. The crack edges are physical details that imply motion and stress. In such places, exchange between subsurface and surface can occur without creating a global signature. Another small payoff arrives. If life relies on sheltered niches, then biosignatures may be subtle and intermittent. The absence of a loud atmospheric imbalance does not strongly constrain the probability of life. It constrains the probability of easily detectable life. The section closes gently by returning to time as an amplifier of quiet processes. With long spans, rare favourable intervals can still happen. With shelter, chemistry can persist through harsh periods. With gradients, complex reactions can keep cycling without needing perfect conditions. The next step turns outward again to how distance and time combine, because the farther a galaxy lies, the more its present becomes hidden behind an earlier light, and that changes what can be inferred about life across cosmic history. A distant galaxy appears as a quiet smear of light, and its colour leans subtly toward the red as distance increases. The early point settles with little effort. Any search for life beyond the Milky Way is also a search through time, because the only messenger is light that arrives late. The galaxy that is seen is not the galaxy that is. It is the galaxy that once is preserved in a moving wave front. At the edge of the glow, the brightness fades through a soft gradient. Dust and gas scatter and absorb parts of the spectrum. The outline of a spiral arm is suggested, then lost. This blurring is not only about optics, it is also about history. Every photon carries a timestamp. That timestamp can be old enough for whole planetary climates to change. A first small unlock appears in the calm fact that the universe offers no instantaneous view. A planet can freeze or warm, an atmosphere can thin or thicken, a biosphere can bloom or vanish. The distant picture would still show the earlier state because the later light has not arrived. The first core concept is redshift. Redshift is the stretching of light to longer wavelengths as space expands. The definition ends quickly. Two plain sentences follow. The spectrum slides and familiar absorption patterns move from one colour band to another. The shift also marks distance and distance marks delay. One sentence closes why it matters. The farther the target, the more the view becomes a record rather than a report. A visual anchor settles on the galaxy's spectrum as a smooth ribbon with small notches. The notches are not perfectly sharp. Their edges are softened by the combined motion of many sources. Some regions of gas move toward the observer, some move away. The blended movement broadens each notch into a shallow dip. This physical detail becomes a quiet clue. The line shape reveals a mixture. It hints at rotation winds and turbulence. It also hides fine structure that might belong to one small place. Another small payoff follows. Large-scale chemistry can still be inferred from these dips. Carbon and oxygen can be recognized. Dust can be estimated. Star formation can be guessed from the balance of blue and red light. Yet life would be different. Life would be a small whisper inside a crowded chorus. The second core concept is temporal mismatch. Temporal mismatch is the gap between when a signal is emitted and when it is received. The definition stays short. Two plain sentences follow. A distant galaxy can host a calm planet now, but the view shows it before calm arrives. Another galaxy can host a lifeless planet now, but the view shows it during a brief habitable interval. One sentence closes why it matters. A negative result in the image does not strongly constrain the present, only the past that is being sampled. A gentle analogy fits this idea without human scenes. A glacier advances and retreats over long seasons, leaving layered ice and sediment behind. A view of the glacier from far away can show one stage. The layers that form later remain unseen until time passes. In the same way, a distant galaxy shows one stage of a long cycle, while later layers of history remain out of reach. A second visual anchor appears as the light of a bright beacon behind the galaxy passing through intergalactic gas. Along the path, a forest of faint absorption lines appears spaced irregularly across the spectrum. Each line is a narrow bite taken from the light by diffuse hydrogen and trace metals in the cosmic web. The pattern looks like delicate scratches across glass. The scratches are thin and numerous. They form a layered map of matter at different distances and different times. Another small unlock follows from the forest. The forest shows that the universe is not a single snapshot. It is a stack of snapshots along the same line of sight. Each absorption line marks a different layer of space and a different age. This matters for life because it reveals how many environments lie between galaxies. It also reveals how much of the observed signal is shaped by intervening material. A biosignature, if it could ever be measured at intergalactic distance, would be filtered through these layers. The filtering would not erase the possibility, it would complicate interpretation. One primary number enters with care. A galaxy observed at a look-back time of about 1 billion years is seen as it was 1 billion years ago. 1 billion years is long enough for continents to drift, for ice ages to come and go, and for atmospheres to transform on a rocky world. This number matters because it makes the delay physically meaningful. A biosphere could evolve from simple to complex or collapse from complex to sparse in that span. The third visual anchor returns to the galaxy itself, now seen as two regions of colour. A compact central glow looks warmer and smoother. A faint outer disk looks cooler and patchier. The boundary between them is not sharp. It is a gradual blend. This physical gradient matters because different regions evolve differently. Central regions can enrich faster. Outer regions can remain gas-rich longer. Star formation can flare in patches and then quiet down. the probability of life can rise and fall within the same galaxy as conditions shift across regions and across time. Another small payoff follows. The delay in the light means that a galaxy's current balance of harsh and calm regions cannot be confirmed directly. Models can estimate, but the view remains historical. This turns the search into a statistical one. The question becomes how often galaxies across cosmic time produce long calm windows for planets. The answer is not pinned to one moment. It is spread across eras. A limit of intuition arrives softly. Intuition expects far to mean elsewhere. In cosmology, far also means earlier. The mind wants a map in space. The sky is also a map in time. This dual meaning can mislead. A bright active galaxy might look promising because it is luminous. It might also be young, turbulent, and chemically immature. A quiet red galaxy might look unpromising because it is dim in starbirth. It might also be old, enriched, and stable for existing worlds. The correction is gentle. Brightness is not the same as habitability. A specific limit of observation follows and remains practical. The blended light of a distant galaxy cannot isolate the signal of a single planet. Even the best spectral measurement returns averages across huge volumes. Dust can mimic aging by reddening light. Bursts of young stars can hide older populations. Intervening gas can add absorption features that resemble local ones. These are not philosophical doubts. They are measurement limits caused by faint photons, overlapping sources, and line-of-sight layering. Another small payoff appears in what this limit still allows. While direct confirmation of life in another galaxy is out of reach, the underlying ingredients and processes can be checked across time. Heavy elements are seen in surprisingly early galaxies. Dust is seen. Molecular gas is seen in some systems. Disks and planets are inferred as natural outcomes of star formation. The plausibility of life can therefore be argued from continuity. The same physics persists. The same chemistry persists. The universe does not appear to change its rules with distance. Only the window changes. A final visual anchor holds on the edge of a distant galaxy, where the light fades into darkness. The fade is smooth and the last photons arrive in a slow drizzle. In that drizzle, the present remains hidden. The past remains visible. The conclusion stays calm. The probability that life exists outside the Milky Way can be high, while direct evidence remains absent because the evidence is buried under distance blending and time delay. The next step moves outward again to the strength of large numbers, because even when each individual world is unknowable, the count of worlds can make expectation meaningful. A wide field of galaxies fills the darkness, each one a faint ellipse, or a thin spiral scattered like quiet embers across a deep backdrop. The early point settles gently. Probabilities become powerful when the number of opportunities is immense. Even if life is difficult, vast counts can make its emergence likely somewhere many times. The scene holds a physical detail that stays concrete. Some galaxies appear smooth and round. Some show faint arms. Some are stretched into arcs by gravity. Their brightness fades with distance through a soft gradient, and their colours vary slightly, suggesting different star populations and dust content. A first small unlock appears in the meaning of variety. The universe does not provide one repeated environment. It provides many experiments running in parallel. Some are rich in metals, some are poor, some are calm, some are violent. If life requires a narrow set of conditions, then only a fraction of environments qualify. Yet the pool of environments is so large here that even a narrow fraction can produce many qualifying cases. The first core concept arrives as expectation value. Expectation value is the average outcome across many trials. The definition ends quickly. Two plain sentences follow. A rare event can be unlikely in one trial. Across many trials, the average number of occurrences can still be large. One sentence closes why it matters. The universe is not one trial. It is an enormous set of trials. A natural analogy fits. In a long coastline with countless tide pools, a rare species might not appear in any single pool. Across thousands of pools, the species can still be found many times. The coast does not guarantee it in every place. The coast makes it likely somewhere. In the same way, billions of galaxies create a coastline of planetary systems. A second visual anchor settles on a galaxy cluster where many galaxies share the same region of space. The cluster has a bright core and a fading halo. Between galaxies, faint hot gas fills the volume and its density falls outward in a smooth gradient. This anchor matters because it emphasizes concentration. Environments are not scattered at random. They can be grouped. In groups, mixing and interactions can alter star formation histories and metallicity. This adds complexity but also increases the number of diverse niches in close proximity. Another small payoff follows. Diversity increases the chance that at least some systems sit in the right window of calm chemistry and time. The second core concept arrives as the Drake-style multiplication, but it stays general and avoids formula. The idea is simple. The number of life-bearing worlds depends on how many stars exist, how many planets exist, how many are suitable, and how often life begins. Each factor can be uncertain. The product can still be large because the first factors are enormous. One primary number enters with care. The observable universe contains on the order of hundreds of billions of galaxies. This is like having hundreds of billions of separate oceans. Even if only a small fraction of those oceans contain islands, the number of islands can still be immense. The number matters because it explains why confidence in not alone can rise even without direct detection. The greatest uncertainty sits in the final factor, the step from chemistry to life. That uncertainty can span many orders of magnitude. The multiplication argument does not erase it. It shows where it matters most. Another visual anchor appears in a star-forming galaxy that glows blue in patches. The patches lie along spiral arms like beads on a faint curve. Dust lanes thread between them. This anchor brings the probability discussion back to physical process. Stars form, disks form, planets form, metals spread, organic molecules appear. These steps have direct evidence in many environments. The remaining unknown is the threshold event. Another small payoff follows. Because several major steps are demonstrably common, the threshold event does not need to be common for life to exist elsewhere. It needs to be non-zero. Over vast trials, even very small probability can produce many outcomes. A limit of intuition arrives softly. Intuition often treats small probability as effectively impossible. Large numbers break that habit. A 1 in a million event is rare in one attempt. Across 1 trillion attempts, it becomes expected many times. The universe supplies more than 1 trillion opportunities when the stars and planets are counted across all galaxies. This does not prove life is widespread. It explains why scientific plausibility can be high without any direct observation. A specific limit of observation follows. The same large numbers that support expectation also hide individual cases. Most worlds are too far and too faint to study. The universe offers volume before it offers access. Measurement is limited to nearby systems and to aggregated properties of distant systems. This means that probability arguments will remain central until technology can isolate planet-scale signals at far greater distances. Another visual anchor settles on a faint gravitational lens, arc a thin curve of light around a darker mass concentration. The arc is smooth with brighter knots. The knots are magnified regions where star formation is strong. This anchor carries a small payoff. Nature can amplify distant light, but amplification usually serves the study of galaxies, not the detection of individual biospheres. The barrier remains. The probability remains. A gentle scale shift closes the section. In minutes, a planet rotates through day and night. In years, it traces an orbit. In millions of years, climates drift. In billions of years, galaxies enrich and restructure. Across these layers, the same chemistry persists. The same physical laws persist. Large numbers persist. The conclusion remains calm. The most defensible statement is not certainty, but expectation. If life is possible under universal laws, and if planets are common, then life outside the Milky Way becomes likely somewhere in the vast count of worlds. The final transition stays soft. The next step gathers the whole arc into a quiet resolution, balancing the high plausibility suggested by large numbers with the strict limits that keep direct confirmation beyond reach for now. The darkness between galaxies looks almost empty until faint filaments and soft glows reveal a hidden structure. The early point settles into a calm final shape. The universe appears able to produce life's ingredients and many potential habitats, while direct proof of beyond the Milky Way remains blocked by distance and signal weakness. A gentle resolution begins with a simple physical image. A filament fades into a broad haze. The haze thins into near black. At the boundary there is no sharp line. There is only a gradient where matter becomes sparse. That gradient is a quiet symbol of the whole question. The transition from possible to provable is also not sharp. It is a gradient set by detectability. A first small unlock appears by separating three ideas that can be confused. Possibility is about physics and chemistry. Plausibility is about how often the right conditions repeat. Confirmation is about measurement. Possibility is strong because carbon chemistry is universal and because planets form as a natural outcome of star formation. Plausibility becomes strong because stars and planets exist in vast numbers across galaxies and because long-lived stable energy sources are common. Confirmation remains weak beyond the Milky Way because individual planets cannot be isolated in the blended light of other galaxies. This separation matters because it explains why certainty can lag behind reason. The first core concept is detectability. Detectability is the ability to measure a signal above noise and background. The definition ends quickly. Two plain sentences follow. A signal can exist and still be hidden by brighter sources. A signal can also be altered by intervening matter and by distance. One sentence closes why it matters. The absence of detection is not strong evidence of absence when detectability is low. A visual anchor settles on a distant galaxy's glow, smooth and continuous like a dim ember. Inside that ember are billions of stars. Around some of those stars are planets. Around a tiny fraction of those planets may be atmospheres with chemical imbalances. Even if such an atmosphere exists, its contribution to the galaxy's light is vanishingly small. Another small payoff follows. The life question at intergalactic distance is not a contest between life and lifelessness. It is a contest between a weak planet-scale signal and an overwhelming galaxy-scale background. The second core concept arrives as inference. Inference is drawing conclusions from indirect evidence using tested physical models. The definition stays short. Two sentences return to plain language. Many facts in astronomy are known without direct images. Star interiors invisible directly are inferred from light and physics. One sentence closes why it matters. Life's plausibility beyond the Milky Way can be argued from universal processes, even without direct biosignatures. A natural analogy fits without human objects. In a deep ocean, currents can be mapped by the drift of floating debris and by temperature layers even when the current itself is invisible. In the same way, the distribution of elements and the behavior of disks can be mapped through light even when planets are not visible. The third concept enters softly as uncertainty. Uncertainty is the range of plausible values when exact numbers are unknown. The definition stays short. Two sentences return to plain language. The probability of life depends most on the step from complex chemistry to self-sustaining biology. That step is not yet measured elsewhere. One sentence closes why it matters. Large numbers of planets can compensate for low probabilities, but uncertainty about that probability remains the largest unknown. One primary number enters as a quiet anchor. The observable universe contains countless stars and worlds across hundreds of billions of galaxies. The exact count is less important than the scale. It is like a night sky made of many separate skies. The number matters because it supports expectation. Even if life begins rarely, the number of opportunities can still produce many beginnings. A visual anchor returns to a spiral arm in a nearby galaxy where dust lanes curve and star-forming knots glow softly. This anchor, ties the entire arc back to repeating processes. Stars form from cold clouds, heavy elements are made and spread, organic molecules appear in dark regions, disks form around newborn stars, planets assemble in rings and gaps, stable stars shine for long spans, water can exist widely. None of these steps appears unique to one galaxy. Another small payoff follows. A universe that repeatedly builds the prerequisites does not resemble a universe designed to prevent life. It resembles a universe where life is allowed, whenever conditions persist long enough. A limit of intuition arrives softly and becomes the final clarification. Intuition often demands a visible sign to accept a conclusion. The cosmic scale denies that demand. The most distant habitats are the least accessible. The largest numbers are the hardest to sample. This creates a quiet tension between expectation and evidence. The tension is not a flaw. It is an honest description of the current boundary. A specific limit of observation follows. For planets in other galaxies, the required contrast to detect atmospheric chemistry is beyond present capability because the planet's light is lost inside the integrated glow of billions of stars. Even with magnification by gravitational lensing, the amplification usually applies to the galaxy's bulk light. It rarely isolates a single planet. The boundary is about photons and separation. It is not about whether life could exist. Another small payoff appears in the near-term path forward. The most realistic approach is to refine the probability question by studying many nearby worlds in the Milky Way. If life or strong biosignatures are found nearby, the inferred probability rises, and by extension the expectation of life in other galaxies rises as well. If many nearby worlds appear sterile despite favourable conditions, the probability lowers and the expectation beyond the Milky Way lowers too. In both cases, the path to understanding runs through measurable samples close to home because the distant universe is too blended. This does not make the question smaller, it makes the method realistic. A final visual anchor settles into intergalactic darkness again, where only a faint filament remains visible. The filament narrows and fades. The scene holds still. The conclusion stays calm and balanced. The universe shows repeated chemistry, repeated planet formation, and enormous time. Those facts support the plausibility of life beyond the Milky Way. The same universe also sets strict observational limits that keep direct confirmation out of reach at present distances. In that quiet balance, the probability is not a dramatic claim. It is a steady expectation grounded in repetition. The darkness does not prove emptiness. It only marks how softly distant truths must arrive. The glow of the filament fades into a thin haze. The haze thins into black.